Okay, here we take a look at a sample problem. So it says the EMF and resistance in the circuit of the figure have the following values of the figure have the following values. Okay, so E1, E2, R1, R2, and capital R. So what is the current I in the circuit? Okay, so this is really easy. Okay, so really easy. So so the only point we need to concern is we have two battery connected in opposite direction. So here you can see this is E1. Okay, this E1 is like clockwise. Okay, like this. Okay, but this E2 is counterclockwise. So they will cancel some of the voltage. Okay, so yeah. Okay, so here, okay, so here actually E1 and E2 will cancel part of them. So E1 minus E2 equals, okay, so for the whole circuit, the current will be I. And yeah, you may consider whether it is clockwise or counterclockwise. So you can see E1 is 4.4, E2 is 2.1. Okay, this one is larger. This one is larger. So the direction, the final direction of the I will follow this one. Okay, rather than that one. So I can quickly determine that I should be clockwise. Okay, so I times this is R1, R2, and R in series. So we have a R1 plus R2 plus R, like this. So I is nothing but E1 minus E2 all over R1 plus R2 plus capital R. So we can plug in the values 4.4 minus 2.1 all over 2.3 plus 1.8 plus 5.5. Okay, so this number is nothing but 0.2408. Okay, so this is really easy. Okay, we only need to consider the series resistance, which is the sum of the resistance, and then this is so there are two EMF connected in series, so we need to determine whether we should add them together or subtract them. Okay, so this is part A. And then for part B, what is the potential difference between the terminal of battery 1? Okay, so actually this is battery 1. Okay, so this is a real EMF. Okay, with a ideal EMF series with a small resistance. Okay, so it asks you what is V, let's say VAB. So this is A, this is A, this is A, so this is B, this is B. Okay, so here we would like to find a VAB, which will be, okay, which VAB will be like a VA minus VB. Okay, so here we can separate into two parts. This one is actually E1. And then also we know that this is I to be 0.240 A, yeah, from question A. Okay, so here from B to the middle point there will be a voltage drop I times R1. Okay, so I times R1. Okay, whether we should add or subtract. Okay, as much as the I is from bottom to top. Okay, so this one is higher, this one is lower, but here will be like A to this point to this point. Okay, this is plus, but yeah, this is higher, this is lower, so we should make it a subtract sign here. Okay, so this is actually E1 minus I times R1, which is 4.4 minus 0.240 times 2.3. okay, which is actually 3.8 volts. Okay, so this question is really easy. Okay, so next we talk about the multi-loop circuit. Here in the textbook it called junction rule, but as I mentioned in chapter 26, I call it KCL, Kirchhoff current law. Previously we have another one called the KVL somewhere here. Okay, this is KVL, the loop rule. And then we also have the Kirchhoff current law. Current law, KCL, not the one in the chemistry class, not the potassium chloride, 氯化钾, okay, 氯化钾. So this is KCL. This KCL is Kirchhoff current law. Okay, so it says the sum of the current entering any junction must be equal to the sum of current leaving the junction. Okay, so actually we have KCL, KVL, which can give you some correct equations. So when I was the TA for the circuit analysis, like 15 years ago. So yeah, so of course the circuit might be more complicated, and then yes, the student can write many equations using both KCL and KVL. Yeah, but actually that's not a good idea to write the equation with both way. For some of the circuit you use KCL will be easier. For some of the circuit you use KVL will be easier. But when you try to use both together, then usually you will have too much equation, and maybe when you make some mistake, then yeah, you have a joint equation. If one of the equation is not correct, then you get the wrong answer. So yeah, so actually you need to know for a circuit how many unknown there are in the circuit. So let's see here. Okay, so let's see how to solve this circuit. Okay, so here the circuit have 4 nodes, A, B, C, and D. So there are totally 4 nodes. 节点. Okay, so so for all the circuit you can just define any of them to be a ground. Okay, design only one of them to be a ground. So let's say we can just make this one the ground. Okay, so this one you already know the voltage should be 0 volt. Okay, so it should not be an unknown. Okay, and then so the only remaining nodes are 1, 2, 3, A, B, C. So 3 nodes. So maybe you consider we need to write three variables. Okay, let's say a VB, a VA, VB, VC. Okay, so let's see if we define this one to be VB, but here we have a 2 EMF. Okay, this is E1, this is E2. Of course you can just define this one to be VA, this one to be VC. Okay, so here we have 3 variables, so you need to write 3 equations, so independent equations, then you can be able to solve for VA, VB, VC. But for this case, this is EMF, this is EMF, which means that the potential difference between VA and VB will be a fixed value of E1. Okay, so usually I will not define VA and VC. I will just make it like this is VB plus E1. Okay, this is negative, this is positive. So I just define this one to be VB plus E1. So this is a known value. Okay, of course when you try to solve this circuit, you should know E1, E2, R1, R2, R3. Okay, all these 5 values should be a known value. Okay, so if we define on this node to be VB plus E1, of course you can just write on this is VA and then VA equals VB plus E1. Okay, this is actually the same thing, but sometimes you may not be so familiar, and then you create one more variables, you have more chance to make mistakes. So usually when we have this case, I just define this is VB and then this is VB plus E1, and then similarly this is VC, so this is just like VB plus E2, and then we will be able to write a single equation to solve the circuit. Okay, so let's see. Because this is VB, so we try to consider this point, okay, using the KVL to write one equation, because we only have one variable VB, okay, which means we need to only write one variable. As I mentioned, although this KCL is like the sum of the current entering must be equal to the sum of leaving, okay, entering and leaving, but usually I will just consider all the current to be going out or going in, or let's say I consider all the current going out, this current, this current, this current, 3 current going out, because we only have 3 lines connected to this node. Okay, so there are only 3 current. I just consider all the current to be going out. So for the left one, this is VB, this is VB plus E1. Okay, actually we cannot determine the current here using the EMF, because the EMF, the characteristic of the EMF is like this is V, this is I. Okay, this is a flat line. Okay, even you know the voltage, you don't know how large the current is. The current can be positive, negative, or even 0. It doesn't change anything, because this is an ideal battery. We may not be able to find the current using this EMF. So actually this I1 actually goes to here. So this is a resistor. So we may be able to find the current using the Ohm's law. So this I1, okay, so I will just consider, okay, I will not use this I2. Okay, I will just define I2 in the opposite direction. Okay, so which means that we should have I1 plus I2 plus I3 to be 0. If you use the original one, okay, I1 plus I3 should be equals to I2. Okay, but usually I just define all the current to be going out or all the current to be going in. Even for the same circuit, you can define going out, going in 2 different ways, but for different nodes. It will be fine. Okay, so here I1 will be this node VA minus this node is the ground, 0. So VA is actually this one, VB plus E1 minus 0. So VB plus E1 over R1. Okay, for the second one, okay, here we cannot determine I2 using this EMF similarly. So here we have a resistor. So this is VB plus E2 minus 0. Okay, so VB plus E2 and then minus 0 over R2. Okay, so this will be I2. And then for I3 from this point to here. Okay, so this is easy. This is VB, this is 0. So VB minus 0. Okay, VB minus 0 is nothing but VB. Okay, over R3 to be 0. Okay, so we can write a single equation. Okay, so here we can just collect the term with VB. Okay, so altogether we have 1 over R1 plus 1 over R2 plus 1 over R3 times VB equals, we just move the remaining 2 terms to the right side, which is this one and also this one, okay, which is actually negative E1 over R1 plus E2 over R2, like this. Okay, so the solution will be nothing but VB equals negative E1 over R1 plus E2 over R2 or over 1 over R1 plus 1 over R2 plus 1 over R3. Okay. So as much as you know VB, then you will be able to find all the voltage here also. This one is nothing but VB plus E1. This one is nothing but VB plus E2. And then you will be able to find all the current I1, I2, I3 by substituting this one back to here. So this is I1. Okay, substituting VB to here. This is I2. Substituting VB to here is I3. Okay. So yeah, so when you try to solve a circuit, you need to know how much variable you should have, and then you write the correct number of equation, and then you can solve it. And after you solve it, you can be able to know everything about this circuit. For example, if you would like to know VA minus VC, is also possible. Okay, so from here to here. Oh, this is too trivial. This is, yeah, even before you solve the circuit, you know, this is VA minus, this is E1 minus E2. Okay, so this is VA minus VC. Okay, but yeah, actually you can be able to know actually this circuit is really easy. Okay, yeah. So yeah, so actually, yeah, we can also use KVL to solve this circuit. The same circuit, you can use as KVL. And when I learned the circuit theory, it will call this will be called mesh analysis. Mesh analysis. And for the KVL, we will call it node analysis. Node analysis. Yeah, because actually when you only know KCL, KVL, you are free to write KCL for a node, or you can be able to write KVL for any loop. So maybe actually you will still get the correct answer if you are careful enough. Yeah, so maybe in a single circuit you write some KCL, you write some KVL, and then you may still be able to solve it. But yeah, so but actually to make it more systematic, yeah, they try to find some method like node analysis. We only use KCL to solve the circuit, and then as I mentioned, yeah, what we concern is the node. Okay, we need to count how many nodes in the circuit. So actually for every independent node, we need to write an equation. So we call it node analysis. Okay, so of course this one, there are 4 nodes, but only one of it is independent. If we define, this is 0, this is ground, and then this is an unknown, this is independent. But here we have 2 EMF, so these VA and VC are dependent to the node VB. Here we can also use KVL. We need to define something called mesh. Mesh, what is mesh? Mesh means we try to define, this is the current for this loop. This is the current for this loop. Okay, so you just try to ignore this I1, I2, I3. Okay, we try to define, this is I1, this is I2. Okay, for this loop. Okay, so here we would like to count how many loop. Okay, we have 1 loop, we have 2 loop. Of course, we don't count this one. This is a big one. We just try to count the smaller one. Okay, without other thing. If you just define this one, okay, this loop are going across this loop. Okay, so we don't count that one. Okay, so here we can define, this is I1, this is I2. And similarly, we can just define, this one to be the ground. Okay, so here, which means that for the mesh, okay, so this is mesh 1, this is mesh 2, this is mesh 2. For the mesh 1, For the mesh 1, we can, let's say we can start from here and then going in this direction, okay. So this is I1 in this direction, just ignore this one. Okay, so I1 going from here to here, so this will be I1 times R1. Okay, this will be our voltage drop because we define I1 in this direction. This is higher, this is lower. Okay, so for this one, this one is higher than that one. This is plus, this is minus. So we should have plus E1. And then going to here. So for this R3, we have I1 in this direction, I2 in that direction. Okay, so we will have I1 minus I2 times R3. Okay, this is a little bit tricky, but yeah, for the middle branch, we have I1 and I2, two mesh going across this one. Okay, so we need to consider, okay, this is the positive direction. I1 times I3. Okay, this is the reverse direction, because when we consider this is the mesh. Okay, this one has the opposite direction. Okay, so we should subtract I2 times I3. So we have this one. And for the second loop, also we start from here. Okay, so here we have I2 minus I1. So for the mesh 2, we have I2 minus I1 times R3. And then from here to here. Okay, this is higher, this is lower, so we should subtract E2. And then going to here, I2 R2 plus I2 R2 equals 0. So actually here we have two unknown with two equations. I1, I2 are all independent variable. Okay, so we need two variables. Then you may be able to solve for I1 and I2 equals something. Okay, finally you will get the same result as this one. Of course, you will be, when you subtract this one back to here, this is actually negative I1. So this I1 has the opposite direction of this I1. Okay, so don't mess up. This is another I1. So this I1 is the negative value of this I1. So if you have interest, you can just try to solve this one. This is not easy. This is not difficult. We only have two variables with two unknown. Okay, so we can solve it quickly. Okay, so next we consider the resistance in parallel. Okay, so here we can see this is an EMF. This is R1, R2, R3 in parallel. Okay, yeah, of course we have not taught it before the experiment. Yeah, but hopefully you know how to calculate the parallel resistance. Okay, so yeah, so here we will need to use KCL. So this is I. Okay, so this I1, I2, I3. Okay, will sum up to be I. Okay, so here I to be I1 plus I2 plus I3. And I1, I2, I3 we can use the Ohm's law. So which means that I1 is V over R1, I2 is V over R2, I3 is V over R3. Okay, so we just substitute it to there, and then we can factor out V. Okay, and then we can have so we can have something like so actually we can just move this part to the other side. We will have something like V equals I times 1 over R1 plus 1 over R2 plus 1 over R3, but take the reciprocal of it. Okay, so So for this one, this is the equivalent one. Okay, we will have V equals I times R equivalent. Okay, so comparing these two, because we want these two circuit to be equivalent to each other, which means that when we have the same E, it should have the same I. Okay, so V and I should be the same, which means that this part should be the same as this part. Okay, this is reciprocal. Okay, so which means that we should have Req to be the reciprocal of this whole thing, or the reciprocal of Req to be the sum of the reciprocal of the resistance. Okay, so 1 over R1 plus 1 over R2 plus 1 over R3. Okay, if we have more than 3, if we have n resistance in parallel, then we should take the reciprocal of them, take the sum, and then take the reciprocal again to get the equivalent resistance. Okay, so this is easy. Okay, so here this is a quick summary for the resistance and capacitance. Okay, so for the resistance, if we have series resistance, we just add them together. If we have parallel resistance, we take the reciprocal and then take the sum and then take the reciprocal again. But for the capacitor, it is the other way around. If we have series resistance, we need to take the reciprocal and then take the sum and then take the reciprocal again to get the series capacitance. And for the parallel capacitance, we just need to add the capacitance together. Okay, so one thing I can supplement here is if we have inductor, parallel inductor or series inductor, okay, which side we should take? So for the inductor, we should take the left side. Okay, if we have series inductor, L equivalent will be summation of Lj, j from 1 to n. And if we have a parallel, and LLEL, parallel, then we should take the reciprocal of the inductance, and then take the sum, and then take the reciprocal again. Okay, so you should take the left side. Later in this chapter, we will talk about the phasor, then you'll know something about that. Not this chapter, it should be chapter 31. Okay, so here is another sample problem. Okay, so it says, okay, so the figure show a multi-loop circuit containing one ideal battery for 4 resistance with the following values: R1, R2, E, R3, R4. Okay, so here we have one EMF and then 1, 2, 3, 4 resistance. Okay, so this circuit is still very easy. So what is the current through the battery? Okay, this is the battery we would like to find. Okay, let's call it I. Okay, so this circuit is easy because we can see R2 and R3 are in parallel. So first of all, we can just calculate R2 parallel R3, R2 parallel R3, which will be 20, 30. Okay, 20 parallel with 30, which is 20 times 30 over 20 plus 30. Okay, if we only have 2 in parallel, R1 parallel R2, which will be nothing but R1 R2 over R1 plus R2, like this. Okay, so yeah, like this, because it is nothing but R1 over R1 plus 1 over R2, and then take the reciprocal. So you will get R1 plus R2 over R1 R2, and then take the reciprocal of the whole thing. So it turns out to be R1 R2 over R1 plus R2. Yeah. Okay, so you should notice that the parallel of it will be less than R1 parallel R2 will be strictly less than R1 and R2, less than the minimum of them. Okay, if we have a, let's say, 2 ohm and 2 ohm parallel with each other, the parallel resistance will be 1 ohm. Okay, if we have a 1 ohm parallel with let's say 1 kilo ohm, okay, this value will be slightly less than 1 ohm, 0.99 something. Okay. Okay, so for this one, this will be 600 over 50, which is 12 ohm. Okay, so here we know R2 parallel R3, and then later on we have R1 series with this R2 parallel with R3, and then series with this one. So the R equivalent will be R1 plus R2 parallel R3 plus R4. So it will be 20 plus 12 plus 8, which is 40 ohm. Okay, so finally we can find IE to be E over the whole REQ, which is, this one is 12 over 40. 12 over 40 is 0.38. 0.38. Okay, so this is easy. Okay, so next it asks you what is the current I2 through R2. Okay, what is this I2? I2. Okay, we already know this is I equals 0.38. 0.38. Okay, so yeah, actually in the circuit theory, I will just remember an equation like I2 to be I times let's say R2 plus R3, and then in the denominator is R3, something like this. This is so-called the current divider. Current divider. Also, we will have something called a voltage divider. Yeah, so voltage divider. So it is just like for parallel resistance. Okay, this is the sum of the current. Okay, so it is divided into two parts. This is I2 and also I3. Okay, I just remember the equation. But of course, you are not familiar with why we like that. Okay, let's see. Yeah, so originally we have I. Let's see. Okay, so for this one we have R2 parallel with R3, and then there will be I going through it. So the voltage across it, let's say this is VB, this is B, VBC here. VBC here will be nothing but I times R2 parallel R3. Okay, and then considering here, VBC will be I2 times R2, will be I2 times R2. Okay, so we can just explain this one to be I times R2 R3 over R2 plus R3 equals I2 R2. Okay, so we can do the cancellation here. R2 and R2 cancel each other. So finally we get I2 to be I times R3, R2 R3. Okay, so which is actually this one. Then we can actually substitute the number here to be I is 0.3, and then times R3 is 30 over R2 is 20 plus 30. Okay, 3 over 5. So this is 3 over 5. Okay, so this is 0.188. Okay, and then it also asks you what is I3. I3 is nothing but I minus I2, which is 0.3 minus 0.18, which is 0.128. Also, you can still use the current divider, which is actually I times R2 over R2 plus R3. But actually you can quickly find that this one and this one will actually add up to 1, so this is actually the same thing. So you also get this answer. Okay, so here we have another sample problem. Let's see. The figure shows a current whose element have following values E1, E2, R1, R2. Okay, so this look a little bit more complicated. Okay, so here it says the three battery are ideal battery. Find the magnitude and direction of the current in each of the three branch. Okay, so all together we have I1, I2, I3. Okay, so here let's try to use the mesh analysis. Of course, you can still use node analysis, but here we can quickly see this is 0. Okay, so this is an independent voltage. This is dependent, and then this is dependent. So actually, we still have two variables if we use the node analysis or use the KCL. Here, let's try to use the KVL or the mesh analysis. So this is I1. Of course, you can define I2 to be like this, but in the question, we already have I2 in that direction. So let's try. We can also define I2 in the opposite direction. Yeah, so this is I1, I2 have the opposite direction. So let's see. For the mesh one, let's start from here. Okay, so here is I1, R1, and then this is E1. Okay, so this is lower, this is higher, so we should have negative E1, and then here I1 times R1 plus I1 R1, and then going to here, this is I1 I2 in the same direction, so we should add them together. So we have I1 plus I2 times R2. And then here, this is higher, this is lower. So we have a plus E2 equals 0. So we can slightly rearrange the term. We have a E1 minus E2 to be 2R1 plus R2 times I1. We have this one, and this one. Okay, so we have a 2R1 and then 1R2. And then also we have plus I2R2, which is actually this one. So for the mesh 2, okay, let's start from here and then going in this way. So the first one is I2R1. And then here, this is lower, this is higher. Okay, so we should subtract E2. Okay, this is E2. Okay, and then going from here to here, we should add I2R1. Okay, and then going to here, I1, I2 in the same direction, so we should add I1 plus I2 times R2. And then here, this is higher, this is lower, so we should add E2. Add E2 equals 0. Okay, so this is interesting because we have a E2 and negative E2 to cancel each other. So in this loop, there are not any EMF remaining. Okay, so here we have I1 only this one. So we have a R2 times I1, and then we have R1 and then R2. Okay, so we have 2R1 plus R2 times I2. Okay, so here we can see we have two variables, I1 and I2, with two equations. So we may be able to solve it. And before solving it, we can just plug in the number to make it easier. So we have E1, E2, E2, R1, R2. Okay, so just plug in there. So we have 3 minus 6 equals 2 times 2 plus 4 I1 plus 4 I2. And then here we have 0 equals 4 I1 plus 2 times 2 plus 4i2. Okay, so you can just somehow simplify it. Negative 3 to be this is 2 times 2 is 4, 4 plus 4 is 8, 8i1 plus 4i2, 0 equals 4i1 plus 8i2. Okay, so you should be able to solve it. I1, I2 to be negative 0.5a, and then equals I2 equals 0.25a. Okay, and then finally I3 is this one, so it will be I1 plus I2. So finally I3 will be I1 plus I2, which is actually negative 0.25a. Okay, so all these three are the answer. Okay, so which means that I1's negative 0.5, which means that this should be in this direction, in the from right to left, 0.5a. And then for I2, positive 0.25, which means that this is 0.25. I3 is negative 0.25, which means that in this direction, 0.25a. Okay, so you can see 0.25, 0.25, finally 0.5 going to this direction. So it doesn't really matter which direction you assume. So as much as you make every step to be have the same have the correct sign, have the correct polarity, then you get the correct answer, even though the answer is negative, which means that it should be the opposite direction. Okay, so let's have a